In this video, we're going to take a look at some key sensor specifications or sensor properties that you should be concerned with when you're purchasing a sensor, using it, or deciding how you're going to set up your sensor connection. I've listed here a number of different sensor specifications that are most of interest to us. There are a couple of these that we're going to focus in on most in this video. Here, we're going to focus most on sensitivity, nonlinearity, and hysteresis. Those are two types of sensor errors. Resolution, accuracy, and offset and zero drift. For many of the sensor properties that we want to discuss, it will help us if we first talk about something called the sensor response curve. The sensor response curve is a plot that shows us the input of the sensor versus the output. Remember that a sensor is a device that converts a physical input to an electrical output. For example, with our photocells, the input is light intensity, such as lux. The sensor output for a photocell is resistance. It's measured in ohms. In order to get the sensor response curve, we have to test the sensor to see what its output is for any given input. The response curve might look something like this. The response curve tells us for any value of sensor input, what would be the expected sensor output. Note that the sensor response curve might be different for the exact same sensor depending upon what we're using that sensor to measure. I'll show you an example for the photocell. Let's suppose that instead of using the photocell to measure light intensity, we're going to use the photocell to measure distance to an object. In this case, the sensor input is the thing we're trying to measure, which would be distance units, like meters. Now, in order to measure the sensor output, we would need to hook up the photocell in a circuit to convert the resistance to a voltage that we could measure. So in this case, the sensor output would be volts. Even though the sensor might be the exact same sensor, the response curve in this case would be different because we're measuring distance versus voltage instead of light intensity versus resistance. Our sensor response curve might look different, maybe something like this. There are a number of sensor properties that we can get by taking a look at the sensor response curve. So now that we understand what a sensor response curve is, let's take a look at some of the sensor properties that we can get from the response curve. First, let's take a look at sensitivity. Sensitivity of our sensor describes how much of a change of the output results from a change in the input. Remember that a sensor is a device that converts a physical quantity into an electrical quantity. So here, the change in the output would be measured in units of some electrical quantity, usually volts. The change in the input would be measured in units of whatever it is we're measuring. For example, if we're using a photocell, the change in the input would be measured in lux, and the change in the output will be measured in resistance units, in ohms. Now, keep in mind that the sensitivity of a sensor might be measured differently depending upon how you're using the sensor. For example, if we are using a photocell to measure distance, as we might be doing in lab, in that case, the change in the input would be measured in distance units, and the change in the output would be measured in volts because we're measuring the output of the photocell with our microcontroller, which measures voltage. Sensitivity is one of the sensor specifications or properties that we can get from the sensor response curve. Since sensitivity is defined as the change in the output divided by the change in the input, the sensitivity can be found as the slope of the sensor response curve. Note that the sensitivity of the sensor might not be constant over its entire range. Sometimes sensors are more sensitive in certain ranges and less sensitive in other ranges. A sensor is more sensitive if the slope is greater and less sensitive if the slope is less. In this example, the sensor shown is more sensitive at the beginning of the input range than it is at the end of the input range. Now, let's talk about another sensor specification called nonlinearity. Nonlinearity is a kind of error that a sensor can have. We can find the amount of nonlinearity error that a sensor has from its sensor response curve. And sometimes it helps to think about nonlinearity error in terms of sensitivity. Nonlinearity error is the amount that the sensor response curve deviates from a straight line. So if the sensor response curve is exactly a straight line, in other words, the slope of the line is a constant, or the sensitivity is constant, then we would say that this sensor has zero nonlinearity error. In other words, if the sensor response curve is exactly a straight line, then it has no nonlinearity error. Now let's take a look at an example for a sensor that has nonlinearity error. If a sensor has some nonlinearity error, the response curve might look something like this. In this case, the sensor response curve is not a straight line. Or, said in another way, the slope or the sensitivity of the sensor changes in different ranges of the sensor input. In order to figure out how much nonlinearity error this sensor has, what we will do is we will fit a best fit straight line to the sensor response curve, and then we will find the maximum amount that the sensor response curve deviates from the best fit straight line. This is the sensor's nonlinearity error. It's best to have a sensor with the most linearity that we can find. In other words, we don't want to use a sensor with a lot of nonlinearity error. When we purchase a sensor, it typically shows the nonlinearity error in its own data sheet. However, the nonlinearity error that is quoted for a sensor in its data sheet is only accurate as long as that sensor is being used to measure what it's intended to measure. If we use a sensor to measure some other property, then we might have to find out the nonlinearity error ourselves by testing the sensor. For example, when you purchase a photocell, the datasheet for the photocell will probably tell you the nonlinearity for the sensor response curve that reports lux, sensor input that is light intensity, versus ohms of resistance, the sensor output. But if we are going to use that photocell to measure distance, we might want to know the amount of nonlinearity error when the sensor is measuring meters of distance versus voltage, the thing that we will measure. In that case, we would need to find the sensor response curve ourselves by testing the sensor, and then use our own plot to best fit a straight line and calculate the nonlinearity error. Now, I'd like to point out that there are a number of different ways that a sensor datasheet might report the nonlinearity error. And I'd like to mention these so that if you see these specified in a sensor that you purchase, you'll be able to know what the different specifications mean. There are at least 3 different ways to specify nonlinearity error. One way is as deviation from a straight line in the input units. In this example that I've shown here, this is a sensor response curve for a potentiometer. It's showing input units of rotation angle and output units of resistance. If the nonlinearity error is specified as deviation from a straight line in input units, then it would be reported, in this case, in units of radians or degrees. If it's specified as deviation from a straight line in output units, then it might be quoted in units of ohms. Or it might be reported as deviation from a straight line as a fraction of the full scale. I'll briefly show you an example of what each of these means. Here's an example of specifying the nonlinearity error in input units. This shows that the nonlinearity is being measured in rotation angle, some number of degrees. And the meaning of that number is that it is the distance between these 2 lines, the distance between the straight line approximation and the actual sensor response curve as measured in the x-axis, the rotation angle. Another way to measure the nonlinearity is along the y-axis, the distance between the straight line approximation and the sensor response curve in output units, in this case resistance in ohms. If we specify the nonlinearity error as a fraction of full scale, the way we would do this is we would take the entire sensor range, that is, in this case, the minimum to the maximum input units that the sensor can measure, and we'd take the nonlinearity in the x-axis, and we'd express the nonlinearity as a percentage of the complete scale. For example, if this sensor shown in this example can measure between 0 degrees and 360 degrees, and if the distance between these 2 lines here is 36 degrees, then we would say that the nonlinearity error is 10% Fs. That is, 10% of the full scale is nonlinearity error. I also want to mention that the way that this best fit straight line is found might be different depending upon the sensor manufacturer. One possibility would be quoted as TSL. That stands for terminal straight line. In this case, the best fit straight line simply connects the minimum and the maximum points in the input units. Another possibility would be quoted as BSL, which stands for best straight line. In this case, the best fit straight line is determined using least square method to find the best fit straight line according to the least square error, or also sometimes people say minimum square error. Either way, you should just be familiar with these terms so that when you see them quoted in a sensor specification sheet, you know what they mean and you can interpret it to determine how accurate your sensor is and whether or not it will be sufficient for your application. Now, let's take a look at another sensor specification, which is also a source of error, called hysteresis. Hysteresis is the amount that the sensor response curve is different depending upon whether you did the measurement starting at the minimum value of the input or whether you measured it starting at the maximum value of input. I'll show you an example. Suppose that you are using a photocell to measure light intensity. When we draw the sensor response curve, the x-axis will be light intensity in lux, that is the input value you're trying to measure. and the output value will be the electrical property that changes in response to the physical property, in this case resistance. Now, when we do an experiment to determine the sensor response curve, we might do this experiment by starting out with the room being very dark and measuring the resistance. We would then slowly increase the light intensity and measure the resistance as we go. So we would come up with points on the sensor response curve like this, starting at the smallest light intensity and increasing light intensity as we go. Then, once we've arrived at the maximum light intensity, we might do the exact same experiment again, except this time we start with the room being at maximum brightness and slowly reduce the light. In that case, we might get a sensor response curve that is different on the way back. For example, our sensor response curve on the way back as the light becomes darker might look something like this. In this case, our sensor has some hysteresis error. The hysteresis error would be the distance between these two curves, the one being the sensor response curve that we obtained by starting at the low light intensity and slowly increasing it, and the other sensor response curve is the one we got by starting at a bright light intensity and slowly darkening. Like nonlinearity error, we would like to choose a sensor and set up our sensor in such a way that we have small hysteresis error. Another sensor property that we're interested in is resolution. Resolution is the smallest detectable increment of the input quantity. In other words, if we're looking at a photocell, the resolution might be the smallest amount of increase or decrease in light intensity that allows us to detect the change in resistance. Note that the resolution of the sensor itself might be different than the resolution of your entire sensor setup. For example, if you are recording the sensor value in a string of bits that has a lower resolution than the sensor itself, you will be limited by the resolution of your measuring device. So resolution is not only a property of a sensor, but it's a property also of your sensor setup. Another sensor property that we're interested in that you might see quoted on a sensor spec sheet is accuracy. Accuracy refers to the closeness of the agreement between the measurement and the true value of the measurement. The measurement is the thing that you are measuring. In other words, given what the sensor tells you is the value of the property you're measuring, how closely does that agree to the actual value of the quantity that you are measuring? Finally, the last property we're going to take a look at here is offset and zero drift. Offset is where a zero input does not equal a zero output, and zero drift is where the offset changes over time, and this is a drift away from the zero offset. I'll show you an example of what this means in terms of a sensor response curve. In a sensor response curve, which shows the input versus the output of the sensor, we would like to have a case where zero input corresponds to zero output. In other words, we want the sensor response curve to intersect the origin right there. If the sensor response curve intersects the origin, that means that we have no zero offset. But this might not be the case. So this case where the response curve intersects the origin is good. It means no zero offset. On the other hand, our sensor response curve might look like this. In this case, the sensor response curve does not intersect the origin. This distance, the point on the output axis where the sensor response curve intersects, that is the zero offset. If the zero offset changes over time, that would be zero drift. Zero offset is not necessarily that bad of a thing. As long as you don't have very much zero drift, then you can know the amount of zero offset and you can compensate for it. In fact, some sensors are deliberately designed to have some zero offset so that you can tell if something is wrong with the sensor if you get a zero output. There are two primary categories of sensors: discrete or digital sensors and analog or continuous sensors. In this set of videos, we're going to look at least one example of each of these two different categories so that you can see the difference between these two kinds of sensors. We're also going to see that even if the sensor is an analog sensor, we're going to have to convert that analog signal into a digital value in order to store the information in the controller. Let's now take a look at a couple of the common types of sensors that are useful to use in robotics. We'll split up these sensors into the two categories that we mentioned earlier: sensors that are used to give the robot information about its own state, and sensors that are used to give the robot information about its environment. Under the category of sensors to give the robot information about its own state, one of the types of information we commonly want the robot to have about its own state is the position of its own joints. For that, there are two types of sensors that are commonly used. The first is the potentiometer. A potentiometer can be used to detect either linear displacement or rotational displacement, and it's the type of sensor that we saw used in both of the types of actuators we've used in class so far, both in the linear slide potentiometer, and the potentiometer is also used in the servos that we use in class. But the potentiometer is not the only sensor that is commonly used to give a robot information about its joint positioning. The other common sensor used for this purpose is a sensor called the optical encoder. An optical encoder does the same job as a potentiometer, but it does it in a very different way. Besides joint positioning, there are some other characteristics of the robot's own state that it might be useful for the robot to have. One such property is the robot's angle of tilt. If we have a robot that needs to balance, either because it's a bipedal robot or for some other reason it has the possibility of tipping over, we might want to be able to measure the robot's angle with respect to the direction of gravity, and for that we can use an accelerometer. To give the robot information about its environment, there are many different kinds of sensors that we could use. Temperature sensors, humidity sensors, anything that's in the environment. There are a couple of environmental properties that are particularly useful for us to get. One of them is the image from a visible light camera. When we start learning about machine vision, we will see that this type of a sensor can give us very detailed information about many kinds of things happening in the robot's environment. The potentiometer and the optical encoder are two good examples to show of sensors that do the same thing, but are different kinds of sensors. The potentiometer is an analog sensor, and the optical encoder is a digital sensor. The difference between an analog sensor and a digital sensor is that an analog sensor can hold any value between its minimum and its maximum. In the potentiometer, the minimum value gives something not exactly but close to 0 ohms, and the maximum value gives something that is close to 10 kiloohms. In between those two values, the sensor can have any value, and so the resolution of the sensor is very high. We can detect even a very small change in angle. The encoder is a digital sensor. It can only measure certain angles. If we rotate the shaft of the motor a distance that is smaller than the distance between the lines, we won't detect that change in angle at all. If we would look at the sensor output curve for both of these sensors, they would look somewhat different. The potentiometer curve would look smooth, but the encoder curve would look like a stair step. Let me show you an example. For example, for a potentiometer, the input is rotational angle, and the output is resistance, which we will convert into voltage. The response curve might look something like this. This shows the relationship between the rotational angle and the voltage as we move the rotation angle from its minimum to its maximum. We would like this curve to be perfectly straight, a perfectly straight line. That would give us a highly linear sensor. But the sensor response curve is often not an actual perfectly straight line. It actually curves a little bit, and that gives us something called nonlinearity error in our sensor. I'm going to draw that on the plot. This dashed line shows the ideal straight line that connects the minimum rotational angle to the maximum rotational angle. The distance that the sensor output varies from the ideal is called nonlinearity. So this sensor curve shows that this sensor has some nonlinearity error. But it also shows that this sensor is an analog sensor because the response curve is nice and smooth. Let's now look at the sensor response curve for the encoder. For the encoder, I've made the x-axis also be rotational angle, but I made the y-axis be counts. The output of the encoder isn't just a voltage, it produces pulses of voltage, one for each pulse of light received by the light receiver. The response curve for the encoder will look something like this. The response curve looks like a stair-step function because of the fact that the y-axis is counts. We cannot have an output from the encoder that is a half a count or a third of a count or some other fraction of a count. We can only have 0 counts or 1 count or 2 counts. We can only have integer numbers of counts. In between integer numbers of counts, we can't detect a change in that particular rotational angle. We would say that the resolution of the encoder is less than the resolution of the potentiometer. The resolution of a sensor is the smallest amount of the input quantity that we can detect. So this distance here, the smallest rotational angle that we can detect, this is called the resolution. For an encoder, we can calculate the resolution by taking the number of lines and dividing the complete angle of one rotation, 360 degrees, by the number of lines. That will tell us the smallest rotational angle that can be detected by the encoder. In other words, its resolution. We're going to look at this concept again when we look at the operation of analog to digital conversion. When we capture an analog value from an analog sensor, we need to convert that value to a digital value in order to store it in our controller and to use the value in calculations. In this video, we're going to look at how this analog to digital version takes place. Remember that an analog value comes from an analog sensor, which means that the sensor can have any value in between the minimum and the maximum value. We see that the value is analog by noticing that the curve of this sensor response curve is nice and smooth. That's as opposed to the digital value, which looks like a stair-step function. The digital value looks like a stair-step because the y-axis is counts. Because the y-axis is counts, it cannot hold a value that is not an integer. In other words, the value from a digital sensor can only be 0 or 1, 2, 3, etc. We could represent the value from a digital sensor as a bit string, because a string of bits can hold an integer value. For example, let's suppose that we want to represent the value from our digital sensor as an 8-bit string, also known as a byte. In a string of bits, each bit can either hold the value 0 or 1. So the lowest value that can be represented is the number 0, where all of the bits are 0. The largest value that can be represented with our byte is the value we get when every bit has the value 1. What number is represented by this 8-bit byte where every bit has the value 1? We can figure this out by adding up the value of each bit. A value of 1 in the rightmost bit gives us a value of 1. A value of 1 in the second rightmost bit gives us a value of 2, double the value immediately to its right. A value of 1 in the next bit gives us a value of 4, double 2. A value of 1 in the next bit gives us a value of 8. We can continue in this fashion to find out the value of each subsequent bit. The next bit is worth 16, then 32, 64, and finally 128. When we add up each of these values, we find that this byte gives us a value of 255. That means that a byte represented by 8 bits has a maximum value of 255 and a minimum value of 0. Any integer number between 0 and 255 can be represented by our 8-bit byte. For example, let's suppose that we would like to represent the value 187 using our 8-bit string. Here's how we would represent the value 187 with bits. We start from the leftmost bit, which is also known as the most significant bit. That bit is worth 128. We're going to ask whether 128 is less than 187, the value we're trying to represent. 128 is less than 187, so we put a 1 for the value in the leftmost bit. Next, I'm going to take the value 128 and I'm going to subtract it from the original number. 187 minus 128 gives me 59. Now, I'm going to take the number 59 and I'm going to look at my next most significant bit. I'm going to ask whether the number 64 is less than the number 59. I see that it is not, so I'll put a 0 in the 64 position. Next, I'll move on to the next bit, which is worth 32. I'll ask whether 32 is less than 59. It is, so I put a 1 in this position. And I'll subtract 32 from the number I have left, 59. 59 minus 32 is 27. So I can now move on to my next bit. I'll ask whether 16 is less than 27. It is, so I put a 1 in the 16 position. And I'll take 16 and subtract it from 27. And I get the value 11. I ask whether 8 is less than 11. It is, and so I put a 1 in this bit. And I subtract 8 from 11. And I get 3. I ask whether 4 is less than 3. It's not, so I put a 0 in this position. And I move on to the next bit. Is 2 less than 3? It is, so I put a 1 in this bit. And I subtract 2 from 3. And I get 1 left. I ask whether 1 is less than 1. It's not, but it is equal to 1. So I get a 1 in this bit as well. I can now check my answer to see whether I have correctly represented the number 187 as a bit string. I do that by adding up the values of all of the bits that have a 1. I take 128 plus 32 plus 16 plus 8 plus 2 plus 1 and check to see whether that is equal to the number 187. When I add up these numbers, I see that they do in fact add up to 187, so I know that I've represented the number 187 correctly in binary. So we see that any value, any integer value between the minimum and the maximum of a digital value can be written as a bit string. That's why having a digital value from a sensor is useful. Bit strings can be recorded and saved and used in our microcontroller. So we want to be able to take an analog value and convert it into a digital value. Let's look at how we do that. To convert an analog value to a digital value, the first thing we need to do is decide how many bits we're going to store the digital value into. In this example, I'm going to assume that we want to store the value as an 8-bit value. I'm assuming this because working with 8-bit values will be useful to us because 8-bit values make up a byte, and a byte of data can be sent at one shot over a serial connection. We now have to find something called the quantization value. The quantization value tells us how much of the analog value output corresponds to a single bit or a single increment of the digital value. We can calculate that value like this. We take the maximum analog value and we subtract the minimum analog value. And we divide that by the maximum digital value minus the minimum digital value. For this example, let's suppose that the minimum analog value is 0 volts and that the maximum analog value is 5 volts. That's a common situation with analog sensors, especially ones that are being used with microcontrollers. We can also find out the maximum and minimum digital values by knowing that we're going to store the value in 8 bits. The minimum digital value will always be 0. The maximum digital value can be found by taking the number 2 to the power of the number of bits that you have and subtracting 1. In this case, I find that the quantization value is equal to 5 divided by 255, which is equal to 0.0196 approximately. That means that when we convert an analog value with a minimum value of 0 volts and a maximum value of 5 volts, any analog value between 0 volts and 0.0196 volts will be converted to the digital value 0. Any value between 0.0196 volts and 2 times 0.0196 volts will be converted to digital value 2. We can write that out mathematically like this. The digital value is equal to the floor of the analog value divided by Q. The floor function means to truncate, that is, to simply cut off any decimal values and leave the integer part of the number only. So it's kind of like rounding the number, except that you always round down and you never round up. So, for example, let's suppose that we're using a 0 to 5 volt analog sensor and we want to convert the analog value 3.2 volts. We've already calculated our Q value, assuming that we're going to store the value as an 8-bit digital value. And we've also made an assumption that this analog sensor can give me a voltage anywhere between 0 volts and 5 volts. We'll now convert 3.2 volts to a digital value. The digital value is equal to the floor of the analog value, 3.2, divided by the quantization factor, 0.0196. When I put 3.2 divided by 0.0196 into my calculator, I get the value 163.2653, etc. because we take the floor function of this value, I truncate the value down to 163. I can now take the value 163 and write it as 8-bit binary using the same approach that we did earlier in this video. Once I've converted the value to its bit string, I've completed the analog to digital conversion.